refraction at spherical surfaces and by lenses. Means here surfaces, earlier we have discussed about the refraction through happens from one medium to another medium, same as here also by using the lenses, means the refracting surfaces are transparent. Then here the spherical refracting surface is a part of the sphere of refracting material. Whatever the material which is the refracting material is there is some of the part is called where the light is incidents and refracts. That part is called as a refracting surface, means a spherical refracting surface. These are all two types of refracting surfaces is there. The first one is a convex refracting surface. Here the convex refracting surface. Convex refracting surface means when the light incidents, the refracting surface be convex in towards the rarer medium. This is a rarer medium and this one is a denser medium. So here it is that here the convex shape is in the towards the refractive rarer medium. This is the refractive surface. So that's why we can say that it's a convex refracting surface. Convex refracting surface towards the rarer medium. The next one is concave refracting surface. Concave refracting surface means the refracting surfaces in which concave towards the rarer medium, towards the rarer medium. The refracting surface is here, so this is a rarer medium, this is towards the rarer medium. So that's why this is a concave refracting surface. First, whenever the convex shape is towards the rarer medium is called convex refracting surface, and if in case of a concave towards the rarer medium, the refractive surface is concave towards the rarer medium is called a concave refracting surface. Then the refraction will depends on that. Some of the assumptions. Some assumptions is the study of refraction based on the some following assumptions is there. They are when the object which has taken to light is incident on the lens or mirror, then that object will be the point sized object lies on the principal axis. Means here this is principal axis. Whenever the object is lies on the principal axis, and whenever the incident ray or the refracted ray both also will make small angles with the principal axis. The angles are very small which is making with the principal axis, means incident ray and refracted ray both are make an angle very small angles with the principal axis, and it's whatever the lens we are taking that the refractive surface its aperture is also small, means the aperture is also small. Here is that when the object is a point sized point object lies on the principal axis, and second one is the incident ray and the refracted ray makes small angles with the principal axis, and the last one is the aperture is also small. Whatever the aperture we are taking that the aperture is also small. The lens, the refractive surfaces aperture is also small. This is about the refraction at spherical surfaces, means the types of refracting surfaces and the assumptions of whenever we are incident, when a point object taken and when we are measuring some of the values, then these are the assumptions which are the object is a point sized object, and also the incident ray, reflected ray makes small angles with the principal axis, and the aperture is also small. So, refraction at a spherical surface. Refraction at a spherical surface means when by taking one surface, means refractive surface, this is the refractive surface, if we are taking that convex refractive surface of its radius r. When a O be the point object is placed at O, the point object placed at O be the point object O placed on a principal axis, and it is incident parallel to the principal axis without any deviation moving in this direction through the pole. So that's why there is no any deviation of the light and moves along a straight line and reflected backwards in that same direction also we can get. And another beam of light ray is incident on the lens means as a refractive surface. On the refractive surface at point B, and refracted on the principal axis, and same as these two rays are meet at point I, where the image is happened, image is formed, that is a real image formed. This incident light making an angle alpha with the principal axis, the object wherever the ray is moving, incident at B making an angle at the alpha, and another light ray this is a normal at point C, and this will be the angle of incidence I, and this will be the angle of refraction R. This is the angle of refraction R, as well as, and this center be making an angle beta, and this one is a gamma. This is the refractive index where the I is formed at the distance of V, means the image is formed. Here that is image is a real image, and according to this we are taking this is a curved surface, so that's why we are taking the at a height of H, which is nothing but HB the height, and object distance from the pole is U. Object distance from the pole is U. By taking these values from triangle OBC, for triangle OBC, because of the incident angle between the OBC with the center, which is this is the normal, so that's why we are taking that from triangle OBC, from triangle OBC, that is I is equal to, means incident angle I is equal to, we can write that alpha plus beta. So alpha plus beta, consider it's equation number 1. Another one is there, the refracting angle, that IBC. So from triangle IBC, we can write that beta is equal to R plus gamma. From that relation is we can write that R is equal to the refracted angle, R is equal to beta minus gamma, taken as a equation number 2. From these equations, I is equal to alpha plus beta, R is equal to beta minus gamma. Earlier the assumptions we have followed that about the whenever the refraction is followed, the some of the assumptions, which is the angles are making very small. Here is that this is the refractive index mu1, and this will be the refractive index mu2. This is the rare medium refractive index mu1, and this will be the mu2 refractive index. By applying Snell's law, we know the Snell's law, that is mu2 by mu1, that is equal to sine of angle of incidence by sine of angle of refraction. By cross multiplying this one, we can get that mu2 sine R, that is equal to mu1 sine I. Mu2 into sine R, by cross multiplying this one, mu2 into sine R and mu1 into sine I. But we know that the incident and refracted angles are very small. So I and R very small, refracted and incident angles are very small, so that's why we can write that sine R, which is similarly equal to R, and sine I, which is nearly equal to I. So we are substituting this one, then we can get mu2 into R, that is mu1 into I. But we know that from equation number 1 and 2, from equation 1 and equation 2, from equation 1 and 2 we are substituting in the equation, consider it's equation number 3. For equation 2, substituting in equation 3, equation 1 and 2 substituting in equation 3, we can get that is mu2 is equal, mu2 into R is equal to, we know that beta minus gamma, that is equal to. Next, another one is I is equal to alpha plus beta, that is mu1 is equal to I is equal to alpha plus beta. Alpha plus beta. So here it is that beta minus gamma is the number equation number 2, and in equation number 1 we are substituting in that above equation. Alpha, beta and gamma angles are small. So we can write that is alpha plus beta is equal to tan alpha plus tan beta. Tan alpha plus tan beta, because of alpha and beta angles are very small, so that's why nearly we can write that alpha which is similarly equal to tan alpha, beta which is similarly equal to tan beta. So alpha is making an angle with the OBP. OBP is the alpha angle making with the principal axis, so that's why we are writing that. We know that tan alpha is equal to means opposite by adjacent. Opposite will be the, this is the H will be the opposite. So here is that H by adjacent be the this one OP. OP means the distance from the object, the distance of the object from the pole. So that's why we are writing that we are measuring the opposite direction to the incident ray. So here we are writing that minus U. Minus symbol indicates that opposite in direction. That's why according to the sign convention. Then plus tan beta. Tan beta means beta is making an angle with that. So here PBC, this is one is also opposite is H, adjacent is a radius R, radius of the refracting surface material R. So here it is that H by R, that is equal to H by R minus H by U. Cancel, it's equation number 4. Next, another one is beta minus gamma, that is equal to tan beta minus tan gamma. Tan beta minus gamma. Tan beta minus gamma means here also we can take that tan beta is equal to, all we know that H by R. We are taking plus R because of we are measuring in the direction of the incident ray. In the direction of the incident ray we are measuring the value. So that's why we are taking that plus R, not minus R. Okay. So in the direction of the measuring, we are also tan beta is equal to in the direction of the material. So that's why tan beta is equal to H by plus R minus tan gamma. Gamma means the angle between this same, also we can write that the opposite is H, adjacent is the distance of the image from the pole, that is V. Here is also, this is also plus V because it is also we are measuring in the direction of the incident ray, means here is also we can take that plus V. So here the H by V. Cancel, say equation number 5, and 4 and 5 equation cancel, say equation capital A. Capital A. So substituting equation 4 and 5 in A, equation A, then we can get that mu2 of beta minus gamma means from the equation of 5 H by R minus H by V, that is equal to mu1 into, we know that alpha beta, alpha plus beta is equal to H by R minus H by U, H by R minus H by U. So by the calculation H can be as common, so that's why both sides H can be cancelled. Then from that whenever we multiply inside the mu2 and is mu1 also, then we can get mu2 by R minus mu2 by V. H taken outside, then H is also taken outside, mu1 multiplied inside, then mu1 by R minus mu1 by U. So H can be cancelled. So here is that H. So after measuring this one mu2 by R minus mu2 by V, mu2 by R minus mu2 by V, that is equal to mu1 by R minus mu1 by U, mu1 by U. From this relation we can write that mu2 taken to this side, then mu2 by R minus mu1 by R, that is equal to mu2 by V is taken this side, then it will becomes minus mu2 by V becomes plus mu2 by V, here minus then mu1 by U. We are taking that here by doing LCM we can get that mu2 minus mu1 by R is equal to mu2 by V minus mu1 by U. This is the one relation that for the refractive surfaces, refraction of surfaces, spherical surfaces, mu 2 minus mu 1 by r is equal to mu 2 by v minus mu 1 by u, means mu 2 be the refractive index of the denser medium and mu 1 be the refractive index of the rarer medium and r be the radius of the spherical surface what we are taking. Then v be the distance of image formed from the pole to the image, then the vu be the distance of object from the pole. This is the equation. This equation also used for the concave mirrors also. In case of concave mirrors, virtual image will be formed. In the case of a convex mirror, the real image formed. But in case of concave refracting surfaces, then here the virtual image can be formed. Virtual image can be formed. This is about a refractive refraction at a spherical surfaces, about that.